Our next speaker is Emilio Maggio. He is head of the computer vision for PTC Vuforia, which is one of the largest augmented reality frameworks and augmented reality software out there. Emilio has a long history throughout his PhD and then also his work later at tracking companies and in Vuforia and with all the various tracking technologies that PTC is working with. And so I'm very happy to have him as a speaker as well in the class. And Emilio, I'll take it over to you.
I mean, thank you very much for the introduction. I really appreciate it, and I appreciate the invite. I hope that this talk is not going to have the stunning visuals of the previous talk, but I hope it's going to be technically interesting and mentally challenging enough for all of you. So let's start. So in general, what is let's give some basics. So what is augmented reality? Is at a very high level is a way to convey some digital information in such a form that is integrated in a seamless way with respect to the physical world. And then here you have some examples of industrial augmented reality. I hope you can see my pointer, where some information about the machineries is shown on the floor, or here there is another example where augmented reality is used by a service and for service and maintenance to help the user, maybe receiving instruction from another remote user, or maybe the system has some information on its own about what needs to be done here on this specific machinery. So in general, if you want to create an augmented reality visual illusions, this can be split in 4 steps. So the first step is you need to sense the environment around you. And you can see that here there are some historical pieces of sensing where a mechanical device was used to track the head of this guy. Nowadays, we are much more lucky and we have cameras on almost every mobile device, so we can create augmented reality experiences at scale. But this could also mean having other inputs of data, like, for example, the Internet of Things, and getting other kind of information, maybe non-visual, coming to us so that we can create this augmented reality experience. The next step is to understand the environment that we see around us. And this, at least for what concerns this talk, is done in 2 ways: by analyzing the video feeds from cameras using computer vision and machine learning. Once you understand the environment, then you can combine it with the digital content that you have and pass this information to the render that is going to create the computer graphics that then you're going to eventually visualize on the hardware, and they're going to reach your eyes. So there are different techniques to visualize augmented reality experience, and this can depend on the platform used, on the type of experience itself. You can have a video see-through devices where the physical world, the data, the light from the physical world comes to the camera and then is combined with the digital computer graphics generated by the renderer, which is overlaid on top of the video feed and displayed on a monitor, and this in this way reaches the eye. This is the case for the AR experience that you can find on most mobile devices, like tablets and phones, and also on some eyewear devices like the Meta Quest. Then you have optical see-through augmented reality, where the digital content comes in the same way as before. However, the light reflected from the physical object reaches directly the eye, but passes through a semi-transparent display where the digital content is added on top of the physical content. And this is the case of hardware like the HoloLens and the Magic Leap, for example. Finally, maybe this is more of a niche. You also have projective AR, where a projector is used to project the digital augmented content directly onto the physical world, and then the reflection of this content reaches to your eyes, so the real and the digital is merged together in this way. And here you have some examples of some projections on buildings and some industrial augmented reality, where a projector shows some information about the interior of the car, or the way it is built. Depending on the type of visualization that you have, there can be also different requirements. So, for example, in terms of latency, if you have something like an optical see-through, since there is no basically barrier to the physical light that comes to your eyes, then also the digital content from the sense into its generation, the rendering and the display need to happen very quickly with very little latency. Otherwise, you will see the two experiences not being in sync and lagging, especially when you're moving. The requirements are more relaxed in the case of video see-through, because the content can always be synchronized at display time. Although this is more true for mobile devices, it's not really true for eyewear, because if content starts to lag, if the video feed lags what is happening in reality, you are going to become motion sick. In general, so when do we want to do with when do we want to apply and this understanding, and what do we want to understand? So we want in general to understand the position and the location of some specific object, like in this case, so there is this gearbox and some augmented reality content is shown associated to it. We might want to understand the presence and position of surfaces, walls, and other things. Like, for example, in this case, we are augmented sofa is shown in a living room so that one can see how it looks like. We might want to track and find the position of the hands to have some interaction with the digital content, and the same is true for tracking the entire human body, so the augmented reality experience can be displayed there as well. For the purpose of this talk, we only deal with the top two subjects. So we look at the augmented reality experience with respect to object and with respect to spaces. So let's just start with some very basics of tracking. So let's say that you have a device that is looking at a table with a camera. And then let's say that we want to display a digital content, in this case is the teapot. What we want to do is basically to define two coordinate systems. We want to define a 3D coordinate system of the plane and a 3D coordinate system of the camera. And then for every frame in a video feed, we want to estimate the relative transformation between these two coordinate systems. This relative transformation, in this case, is composed by rotation and translation, which has in total 6 degrees of freedom and is often referred as a pose. If we do this for every frame, and then we pass this information to the renderer is going to be able to display this content in such a way that it looks anchored to the reality. And if it's also you have a very good renderer, it's going to really look like immersed in the reality environment. How do we compute the pose? So let's say that we have an object. And on this object, we can define a set of these points. So each of these points will have a 3D coordinate in the coordinate system of this object. And for each of these points, we can localize them in the image. You can see the blue dots. And to each of these points in the image, in this case, we have a 2D coordinate. So for every point on the object coordinate system, you have the equivalent point in the image coordinate system. And so for each of these couples, which we call it a correspondence, if we have at least 3 of these correspondences, then we can estimate the pose of the object, so the relative transformation between the object and the camera coordinate system. So Nowadays, we can easily create a mobile AR experience using commercially available tools, but how all this started? The first popular camera-based tracker working on reasonably available commercial hardware were based on fiducial markers, and this is how a fiducial marker looks like. So the idea was that there were severe limitations. This was in the 90s with respect to the cameras and the hardware they were running. There wasn't much software available at the time. So there was, let's design an object which is as easy as possible to automatically localize and track and really stands out from the rest of the environment, is high contrast, and can work in different illumination conditions, and can produce robust and accurate poses with very simple and fast algorithm. And the algorithm was really very simple. So you take this image, you binarize it. So you take the dark pixels, you make them black. You take the bright pixel, you make them white. Then at this point, you have extremely high signal to noise ratio, and you can find the lines. And then you're looking for 4 lines that form like a square under perspective transformation. And then once you have found this line, you can look at the 4 crossings of the lines. And these are basically what your 4 correspondences. And you can use these 4 correspondences to compute pose and show the experience. These fiducial markers are still in use today. Most AR SDKs have their own variant. Even Vuforia, the one I'm working with, has its own. Nowadays, you can do the same even with QR codes. So they've been very successful in kickstarting the entire augmented reality movement on mobile devices. But the goal is clear. We want unobtrusive augmented reality on everyday objects and spaces with minimal setup. So the idea of putting markers everywhere definitely doesn't cut. So how we go from this to our final goal? So for tracking in the wild, a lot of the modern pipelines are based on what is known as natural feature. So let's say that the goal is to find a geometric transformation between the 2 images. The idea is that to find this transformation, we are looking for some discriminative salient regions in this image. And these salient regions are discriminative, and also they can repeatedly identified across different viewpoints, like you can see in these 2 images, across scales. So it doesn't matter whether you are close to the object or a bit farther away. And also they are not sensitive to illumination condition. So in general, it's not a good idea to take a complete textured area. You look for areas where there is some information, like the pinnacles or the entrance of the rat house here in Vienna. So how do you go about detecting these natural features? So if you have an image, a typical way of doing it is to convolve it with a set of filters. A popular filter with this is the logarithm of is the Laplacian of a Gaussian. And here you can see it is a 2D filter. You can see different versions of it with different sizes. And then if you apply this filter to this image, you obtain something like this. In a set of images where in regions with no texture, there is basically no response, and in the other regions you have peaks. So you can see that the filter, the narrower filter, it sort of highlights some finer details, while the larger filter highlights some larger details. So now if you look for maxima, from local maxima and local minima in this space, in the space of the images, but also in the space of the scales of the filter, then you can, and these local maxima are what you define these natural features. And then you can see an example of a detection. You can see a lot of those circles. Some are bigger because they are features from the larger scales, and some are smaller. So once you have detected this feature, then you want to associate a description to this feature. So what you do, you take a region centered on the detected feature, and then you convert this region into a descriptor. So you want to find a representation for this image patch that is descriptive, but at the same time is invariant to illumination, viewpoint, but it's also fast to compare descriptors of different patches, and is also has a small memory footprint. In theory, what you could do, you could just take and concatenate all the pixel values within a patch, but it's not a very good idea because this is representation is extremely variant to illumination, for example. So what you do typically, these are just two examples of popular representation. You can take the patch, you can compute the gradient, and now the gradient for every pixel is going to have a direction and a magnitude, and you can build a histogram of the gradient directions. So you can build this histogram for different subregions, and now you concatenate all these histograms and obtain a descriptor that in the specific case of SIFT, in the normal case, it tends to have 128 floats. Or you can also create a binary descriptor. This is done by doing binary tests. So you take two random pixels and then you assign a 1 if the luminance of this pixel is higher than the other one, and assign 0 the other way around. Then you repeat, you take this set of random pixel multiple times, and now you have a set of 0 and 1, and this is the descriptor. So if you now try to match, so to find the descriptor which has to find the patch that has the closest descriptor between two images, then you usually obtain a result like this, which is not great. So you can see there are some trends. So there are some features detected on the face that are matched on features also here on the face, but there is also a lot of noise. And this is not good if you want to estimate a pose out of them. So what you typically do, so let's try, let's see at a much simpler example. So if you want to fit a line on a set of 2D points, and then you have, let's say, 3 outliers, if you fit using all the data, you obtain this kind of red line. If you fit only using clean data, you obtain this other line. So how you go about getting the green line and not the red one? A popular approach is to first pick at random 2 points. So you know that this is the minimal number of points that you need to fit a line. Then you put some kind of bounds of error, and you look at how many other points agree with this line. In this case, it's 3. Then you repeat the process for other 2 points, you obtain another line, and in this case, you have like 3 inliers. Now you repeat the point, and now we got much luckier, and we got 11 inliers. And this, we take that this is a good solution and say, okay, this is our solution, we are fine. This is the representation of a simple problem in 2D, but the same can be done to poses and higher dimensional geometric transformations. And this is the typical result that you get. So you can see all the outliers have been cleaned up, and only the good correspondences are left, of which we computed a transformation of this image that is represented by this rectangle, white rectangle. So how do you apply this to augmented reality? The first way that this was done is what they are called image target. And the idea of image target is I take a reference image. Now it's just not a fiducial market. This can be any arbitrary image. We perform the feature extraction according to the rules that we have defined earlier. And now we have a set of descriptors. So we associated position in 3D. And these form our target database in practice. This is done offline. Then live on the camera feed, we get an image. We perform the same feature extraction. We extract the descriptors, and now we do matching between the descriptors extracted live and the descriptors that we extracted offline from this image. Then we apply robust model fitting. We compute the pose, and we get an augmented reality experience. So this is an example, a nice example of an image target experience, augmented reality experience. I hope you can see it. So what the developer did, so they added an augmented reality twist onto a coloring book for kids. So AR experiences based on image targets and on printed material are still quite popular, but how we extend this to the third dimension, how we do this on standard objects. The thing is quite simple. So imagine let's assume that we have an object and we have a set of images of this object of which we know the relative pose between each image and the coordinate system defined on the object. Then we can simply extract the descriptors and the feature exactly as we have defined for the image targets, and then we just accumulate, or we just put all the descriptors together into a target database, and this is going to be our target definition. You can see that, for example, there are some points here that are seen from multiple views, and these points are going to have more than one descriptor, as is shown here. So there we have seen the practical, how a target is defined, but how do we go and create it in practice? There are a few different options. One option is to use a photogrammetry tool like Colmap or reality capture, etc. Photogrammetry tool typically takes a bunch of pictures and then estimates the pose of all these pictures with respect to each other and computes a 3D reconstruction of the scene. This is usually a sparse reconstruction, but anyway. The other option is to use a 3D scanner like a Matterport and Navis. In this case, you will have the 3D of the object is going to be defined by the reconstruction provided by these tools, while these tools also capture like panorama images that can use to extract features from. The other option is to generate the target live, and this is what happened most of the happen on devices like the HoloLens, the Magic Leap, and this is also what augmented reality toolkit like ARKit and ARCode do all the time. And this is very useful, the ability to generate a trackable target on the fly to generate this kind of instant augmented reality experience, like the one we talked before, like displaying some furniture in the room. We don't want to create the target to then do this after effect. So let's see at a visualization of how the target is created live. Here I'm showing, so the live target generation is also known as the SLAM problem. So this means a simultaneous localization and mapping. And let's see if I can start the video. Nope. Okay. Okay, I wanted to show a visual representation of how the target, how the features are created and mapped in the environment, but we can also see how a camera-only mono-SLAM architecture works in practice. So it's usually composed by two parts. There is a tracker and a mapper. So the tracker, given an existing map of the environment, so given a target, is able to compute the pose of the device. This is the same as we have seen for the image target case. And then there is a mapper that takes the information from the tracker and expands the map and generates the target on the fly. So in general, having a camera-only SLAM has some severe limitations. So for example, not all kinds of motions allow to generate the target. So for example, to generate the target, it's a baseline, so a parallax between the frames is necessary so the depth of the scene can be estimated. So for example, if the user does a rotation around the axis of the camera, then it's not possible to estimate the depth of the feature, and then the tracking experience stops. Definitely, if you only have a camera-only experience, then you will experience unreliable tracking in texture-poor areas. A mono-SLAM system also has no notion of scale. It's not possible to estimate scale from images alone. So from an image, it's not possible to know if you have if you have a small table very close to the camera, or if you have a very big table far away. The other problem is that the map is not gravity aligned, so it means that it's going to be hard, for example, to figure out, to generate an experience that is coherent with the environment. So there are several solutions to these problems. It's in general to add more sensors to the camera system. One way is to add a stereo pair. In this case, you can obtain robustness to other motions because the depth of the scene can be estimated directly from two images from the stereo pair. You can get scale as well. You can have a depth sensor, which also solves the motion problem and the scale problem, and also helps with tracking in texture-poor areas. You can have a fisheye camera that has a very wide field of view, so that it's less likely that you will end up looking at only regions that have no textures. And you can add an inertial measurement unit, so an IMU, composed of usually of a gyroscope, an accelerometer, and this is going to improve all the aspects of the tracking, like robustness to motion, improving texture-poor areas, because you can rely on IMU information. You're going to get the scale of the environment from the accelerometer, and you also get gravity from the accelerometer as well. So typically, if we look at commercial device trackers, what we see is that on mobile devices, they use a single wide-angle lens camera, and plus they integrate this information with the IMU. For more robustness, eyewear like HoloLens 2 uses 4 fisheye cameras. It has a very high accurate IMU, plus it uses a depth sensor as well. All the techniques that I've described so far are the basic of many tracking-based AR experience. Still, many of the most interesting AR use cases happen outdoor in large spaces. And tracking algorithm has to confront significant harder challenges compared to well-prepared room size indoor environments. And so what are these challenges? So if you go outside, especially, you can find a lot of similar repeated textures, especially in building, or for example, in airports. If you look at the scene, the airport might have multiple places that look the same like this. You can have changing environment, like even in an office, you will have some objects that are not good for tracking because they might move. And if you create a target at a certain point in time, this might be completely outdated by the time that you want to use it. The light conditions, especially outdoor, can be changing. And the same about the variation in environment caused by the season. So if you create a target in summer, then the scene might look very different how it looks in winter. And then especially if you want to expand the experience to very large spaces, then you have to deal with the limited resources of modern mobile devices in terms of storage, RAM, and CPU. So what are the things that we can do? If we revise a bit the existing pipeline, so you take a camera, you do feature extraction, matching, and model fitting to get a pose, what you can do, you can use modern machine learning to try to solve this problem. So what you can do in general, you can take the entire pipeline and replace it with a neural network. So instead of extracting feature and storing the target descriptor, one can train a deep network directly on the target keyframe and associated poses. And at test time, the network takes the input as a query image and regresses the pose parameter. Unfortunately, this kind of approach hasn't really worked out very well. The issue is that this kind of system works quite well when at test time you walk on a path that is very similar to that is very well covered by the data that you have at training time. But for example, if you start to go further away, or if you see some area from a different angle, the network, at least in the specific case, doesn't seem to learn very well about geometric reasoning. So it doesn't generalize as expected, and also is not as accurate as a feature-based pipeline. The problem is, again, is that we are asking deep learning to learn about geometric reasoning. And since we know very well how to do geometric reasoning, maybe this is not just a waste of resources, but that's probably not a great idea as well. So other things have been tried is to replace the feature extraction with a deep learning pipeline. So at a high level, the idea is to use a network to map patches onto a descriptor space where patches from the same physical feature on the object are close in space, and patches from different features from different parts of the object are far in the descriptor space. The goal of the network in this case is to generate good descriptor, but they are still too invariant to illumination and viewpoint. So it's about learning about invariance. In general, so you take a patch, you use a convolutional neural network that generates a descriptor to train this space. A triplet loss is used. And then what you do typically is that you take a batch of those patches, of which there is a true positive and several true negatives, and then you create a loss that tries to minimize the distance between the true positive and maximize the distance between the two negatives. These kind of algorithms have been tested quite a lot, and they are already providing significant performance improvements. So here you have some results showing the mean average precision on a popular test set, and this is the baseline. That is the SIFT algorithm that we described, the SIFT feature that we described at the beginning, and this is a set of trained descriptors which provide significant increase in precision compared to the baseline. But in many cases, the patch information is not sufficient. So if this is your query patch, it's very hard to know where it comes from and what is the right match. Because, for example, in this image, these three pinnacles look more or less all like the same. So context is important. You need to look at the bigger picture to understand which one it is. For example, you want to know where this bigger tower is with respect to these other patches. And this has been worked on, and the idea is to not only replace the feature extraction with a neural network, but also replace the matching part with a neural network. Let's go quickly on how this works. So if you have two images where you have extracted some feature and you have some descriptors, this could be deep descriptors or it could be some standard SIFT descriptor. The first you encode the position of these features in the descriptor itself. So you perform positional encoding. Then the next part, you have a graph neural network. This can be, for example, a transformer. And you now use self-attention and cross-attention in a concept in a special way. So the self-attention encodes information related to the relative position between the features and their descriptors within the same image. The cross-attention instead encodes the information on feature across the two images that you want to match. And the result of this network is a new set of descriptors that now not have only information of the patch, but also have information about the other patches in the image. Then you have a differentiable matching layer that is going to return a matrix of how good one of the patches, one of the descriptors on one image matches the descriptor on the other image. And then given this matrix, it's quite easy to find a set of correspondences. So this is what you typically get. This is an algorithm called superglue. And what you get, so this is the results of the correspondences without deep matching, and this is the results of the correspondence with deep matching. So you can see that the number of outliers is significantly reduced, and also the number of correspondences is significantly increased. And this is also reflected by the benchmark. So if you do SIFT plus nearest neighbor, you obtain the area under the curve in this case of around 20%. And then if you use a learned descriptor plus the nearest neighbor matching, you obtain improvement. But now when you use a deep matching like superglue, and then it is another one called LOFTER, you obtain another significant improvement in the results. So in case you have a descriptor-based pipeline, the ability to match is not the only problem you have, especially if you want to scale up your experience. Typically, we extract around 50 to 1,000 descriptor per image, per keyframe that represents the target. And then if you have a target with many keyframes, then matching gets harder and harder because you have many descriptors, and so you are more prone to false matches. Typically, so if we look at this for a room size environment, one will have something in the order of 1 to 10,000 descriptors. For an office, this goes between 50 and 100 and 1 million descriptors. And for a city like space, you have 10 million to 1 billion descriptors. And that's a lot also in terms of storage space and ability to load them in RAM for efficient matching. So there are several techniques that can be used to compress them up. So the idea is that maybe we don't need all these descriptors. We want only to retain the ones that are considered important, or they are the ones that are likely to give us the most of the performance. So in general, we talk about two concepts. One is structure summarization. So where we only want to keep descriptors from 3D points that are visible from many views. So if a 3D point is only visible from very few views, it's unlikely to impact the overall performance, because even when you go at query time, so at tracking time, it's very unlikely that you are able to see it. So in this case, if we count, for example, from how many keyframes a certain descriptor is possible, we can say, let's filter out all the descriptors that are only visible from a single keyframe. The next step that we can do is instead appearance summarization. In this case, what we want to do is that we take the descriptor originated from a single 3D point, and we want to either cluster them and use the center of the cluster to replace a bunch of the descriptors, or we maybe want to fuse them and use a deep network that is able to extract, to combine this information, so to retain some ability to match the descriptor across viewpoints. In general, combining appearance summarization at solving the scalability problem in terms of size is to have some external form of rough localization. So we can integrate our camera-based tracking system together with some other signal, localization signal, for example, coming from a GPS or from indoor, a set of Wi-Fi or Bluetooth beacon. So what you can do, you can take your target, you can split it in region, you can tile it, and then you will have the descriptors of the target split by region. And then when a prior information about the position come with some uncertainty, you can decide to activate only the descriptor from that specific region. And this allows scaling. And you use only those descriptors here for matching. Another approach, let's say that that an external source of localization information is not available, you can also use computer vision to solve a problem and improve the scalability with respect to size. So, and you can use to do this image retrieval. So the problem here is that given a database of keyframe images and a query image, the goal is to retrieve from this database images those who belong to those who were taken from a similar location than the query image. This problem is very similar. This image retrieval problem is very similar to the natural feature descriptor now, so we can still use descriptors, but the descriptors now represent the entire image, not just a small patch of the image. And the same technique applies. So the descriptors are embedded in an image representation space. You can use a deep network. You can train this network with triplet loss similar to the rest, and then you will have a database of image descriptor, not patch descriptor, that are matched against the descriptor for the query image, and you typically obtain a ranked list of results. And this list of results, you can use it because typically to each image you will have associated the location. You can use it to set a prior in a similar way than the external localization system. So some remarks. So we have seen that natural feature pipeline are the backbone of tracking for AR, at least for objects and spaces. That deep learning has provided significant performance improvements over the year, but caution is needed when we try to apply deep learning to geometric problem. And I think this is also valid beyond the augmented reality and tracking. It's also valid for other situations. So if you have a problem that has well-defined physical laws, that follow well-defined physical laws, is usually a waste to use machine learning to learn these physical laws, because you already know them, and it's very likely you are actually going to lose accuracy. Feature-based targets anyway have some limitations. So since they rely on the appearance of these patches, they tend to work not very well on metallic and on objects that have metallic and shiny surface, and especially if you have objects that are mostly textureless. So this brings us to the next quick last topic that I wanted to cover, and the tracking of industrial objects. So the commonality of all these objects is that a model of this object exists, that is the CAD model that was used to design the object in the first place. So here, let's cross a finger. Okay, no, this video is also not going to work. No, yeah, it does. So here you can see, for example, a augmented reality experience where the input was the CAD model of this engine of a motorbike. You can see this was done, I believe, was for an expo. So when they wanted to show this motorbike was launched at the expo, and they were showing, for example, this explode model of how the internals of the engine work. Clearly, you can find more serious application of this kind of technology. So what is the main feature of tracking with CAD? What is the main problem that you need to solve when you do tracking with CAD models? Is that most of the CAD models do not include information for realistic rendering. So if you had a model with nice texture and everything, if you have extremely good renderer, you could basically generate the keyframes and extract natural features from it. But CAD model, that's not what usually happens. For example, this is a CAD model for 3D printed objects, and the colors have nothing to do with the model itself. Also, we have no idea about the material. So the only thing that the CAD model defines is the geometry of the object, and that's what we need to rely upon. So one of the first methods that has been used to do tracking on CAD model, and this is quite another method from the 90s, is based on edges. So the idea is that if I know the pose of the object coming from the previous frame, I can render the edges using a special, using a special shader on the renderer, really as they would appear on the pose defined here, and then I compare this rendered image against the image that we get from the camera. In this case, what you do an edge search. So for each edge, you try to find an edge nearby in the camera image, and then you will have a set of edge correspondences. These work very similar to the feature correspondences. You can do model fitting. If this fitting is not good, you can go back and then use the pose to refine. You render again, you try to fit again until you compute, you get the pose out of it. And the same can be done for initializing the system. So typically, the most popular technique that was used with CAD model was the detection with gradient template. The idea is that a template, basically, it's a view of the object, is a representation of the object from a certain view. You take your CAD model, you render it in different views. Now you look at the silhouette and you extract an array of positions and directions of the silhouette. And then what you do for each of these, we call this set of position a template. And then what you do, you slide this template across your current image, the gradient image coming from your camera, and then you try to find a good match. And you repeat this for all the views. You do this a brute force search, and reasonably tends to work. So here is an example of a video showing a detection based on template matching plus some tracking based on edge tracking. So classical techniques like this work, but they have severe limitations. So much as the edge-based technique look for positive evidence, can be easily distracted by texture in the background. The edge search for tracking is local and can easily result in false matches, either on the background or on, for example, parallel lines that might exist on the object. Template-based detection false positive rate increases with the number of templates because you have to try many combinations. And also the computational cost is linear with the number of templates, and it's hard to cover an object from many points of views. The issue here is that each template is independent on each other. And so even if two templates represent close views, they don't share any information across each other. So the information that you find on the CAD model in terms of edges is locally weak. So we need some kind of global method that can look at the object as a whole and the image at the same time. So one advantage of CAD model is that we can generate synthetic data. And we know that, for example, that in deep learning, amount of data for training is king. And here we are lucky, we can generate as much data as we like. So given a CAD model, we can render it into different point of views under different colors with different backgrounds. We can simulate occlusions and all the rest, and then use it to train a deep system. So what do we use this for? So if you get an input image, you can train a deep network, for example, to recognize which object is in front of the camera. You can train another network to perform a pose estimation. And you can train another network to do the tracking part. So you replace the edge search with a model with a network that takes as input the camera image and takes as input a render view of the object and produces the pose associated with the current frame in a very similar way as the edge search was doing. So here I want to show a short video of how a system works which does all these things using different deep learning components. And then you can see you can recognize different objects. These are mostly textureless objects, so feature-based detection tracking wouldn't work very well in this case. And then here you can see also that the system can recognize the state of assembly of this model, and the tracking advances to a different state as the user assembles the objects, the parts of this model. A very final piece is that based on CAD models, you can also try to train a model to track not specific objects, but object categories. So let's say that you want to create an AR experience on a photo camera, but you want to do it on all kinds of photo cameras. In general, the topology of a photo camera is very similar across them. So you have a lens in front, you have a body. So given this kind of object, which have a reasonably well-defined topology, you can also define a canonical 3D coordinate system. And then you can train a network that for each pixel predicts whether the presence of the object and predicts a 3D canonical coordinate. So what happens, so for each pixel, now you have a 3D coordinate. So in practice, you have a correspondence. So a correspondence from the 3D canonical coordinate to the pixel space. And we know that if we have 3D to 2D correspondences, we can compute poses out of it. So I ran through all the tracking techniques that I wanted to go through, and I have some final remarks. So tracking is already a building block of transformative augmented reality experience. You can do assembly as a service. So with some products, for example, from PTC, you can show in context information. You can actually do navigation in indoor spaces, augmented reality-based navigation. But there are still many open challenges. For example, the long-term target performance, it's unclear. So far, many experiences haven't been deployed for so long that this has been a problem, and many are still in prototyping phase. But these are problems that are going to be faced when you eventually have a long-living augmented reality experience. We didn't treat it here, but you have objects which are not rigid, and then the estimation just based on the pose is not enough. You have deformable articulated objects. As we have seen, it's possible to do very accurate tracking on objects where the topology is well defined, like human body, hands, or we have seen the example of the face in the previous talk. But for industrial objects, the topology can be very variable. You can have a robot arm, you can have some machinery that has some joints. So we need to find a way to represent all this information and be able to train system based on these, or have the ability to detect, for example, this kind of articulated articulations on the fly while tracking. And overall, tracking is just the base for successful augmented reality experience. So with some exception, like, for example, like indoor navigation, then the rest of the tracking is just a tool. So you need a deep integration with other agents and other data sources to make a meaningful AR experience. For example, with IoT, you need to understand the user behavior and interaction and see how this affects, for example, tracking performance, or, for example, how this is impacted by the limitation of the current tracking model. So overall, thank you very much for listening to this long and detailed talk. I hope you appreciated the content, and I'm open to any question that you might have.
Wow. Emilio, thank you so much. That was the first time that I'm not a computer vision person. It was the first time that I got from A to Z in one talk. You basically gave us a whole semester in computer vision here.
I hope you get a high mark.
Thank you. Let's see, are there any questions in the room?
That was an excellent talk. Valentine's right. It just covers so much span by how people really do computer vision for location of things. It's wonderful. And it spends a lot of time too. It's kind of development for age. Wow. Yeah, I was saying it's a wonderful talk. I agree with Valentine. All the span of from the beginnings of this and the fundamentals all the way through deep learning and beyond. My question kind of relates a little bit. You talked about other sensors. When we look at different sensors on platforms nowadays, of course, the phone has almost everything, but there's always something new. Ultra wideband is another thing, right? We can start using radio location to locate certainly mobile platforms. The iPhone already has fairly evolved UWB. It's somewhat accurate orientation. can you, are AR frameworks starting to take that into account as well?
We are definitely, yes. I think, for example, the Vuforia framework now has a deep focus on industrial augmented reality. So there are questions of whether some of these external localization tool can be available. Overall, my thinking is that these tools offer very good localization. Some they also offer not just the positional localization, but also orientation. The question whether this orientation is actually accurate enough for the AR is different, because maybe computer vision based localization is not absolutely accurate, but since it basically matches the image data, then you have quite a good guarantee that the content that you're going to render, especially in video see-through AR, is going to be aligned. Now, in the case of, for example, ultra-wideband, this is not the case. So even like a small error, like of a few degrees, then this can result in a significant misalignment of the digital content with respect to the where you expect it to appear. So maybe at the high level, maybe it can also be used directly for AR, even without vision up to a certain extent, but not for this kind of fine-grained alignment, at least at the moment. Then you need the...
Yeah, when you situate something, then you really do need the precise alignment to the image. That's very true.
Yeah, especially if you want to do like industrial AR, where you want to show some kind of indication, okay, please press this button, and the button is about like 1 or 2 centimeters wide. Then even one angle to the angle degree at 1 meter distance, that's a significant, that can be a significant error. You might point to the wrong button in practice.
It's true. So cameras are here for a while.
Yes, they're here to stay at least.
Very nice.
Cool. Any other questions? Yeah, we're in the interest of time. Emilio, thank you so much for giving us this really comprehensive presentation. And I see you on the other side, internal.
Bye, and thank you for having me.